Hi, this is the lesson on the hypothesis testing comparing two means. And this is called this is also called the independent samples t-test or the two-sample t-test. So last week we were comparing mu to a constant value or p to a constant value. This week we're looking at comparing two group means to each other. This is extremely useful as a hypothesis test, and it's one of the most common hypothesis tests used in the real world. So, some background information. Just like with the other hypothesis tests, there were three different possible sets of hypotheses. For all of them, the null hypothesis is that mu1 equals mu2. This is group 1 and group 2. So the null hypothesis is that the mean of group 1 is the same as the mean of group 2. The alternative hypothesis is either going to be mu1 less than mu2, mu1 greater than mu2, or mu1 not equal to mu2. And just like before, the not equal to is called the two-tailed scenario, and that's important because it comes up on SPSS. And then these other two are one-tailed tests. In StatCrunch, they don't show you the hypotheses written the way I've written them here. They show you an equivalent form, but mu1 equals mu2, if you subtract mu2 on both sides, is the same as mu1 minus mu2 equals 0. And then the same thing goes for whatever this inequality is. If it's less than, greater than, or not equal to, mu1 minus mu2 is the same inequality compared to 0. Okay? Alright, so let's look at our first example. We want to test the usual wisdom that you should eat breakfast the morning of a big test. So we take a sample of high school students and we randomly assign them to two groups. One group is supposed to eat breakfast before taking a sample SAT, and the other group is not going to eat breakfast. And so we say that we have 25 students in each group. It's not necessary to have the same number of students in each group, by the way. So the results are the group that didn't eat breakfast had a mean score of 418 with a standard deviation of 56. The group that ate breakfast had a mean of 438 and a standard deviation of 49. And they're asking you, using a 0.05 level of significance, test whether the students who eat breakfast score higher than those who don't. So we're going to label the two groups. We'll call them group 1 and group 2. And just to keep things simple, the way I usually do the labeling is whatever is the first group listed in the problem, I call it group 1. So group 1 didn't eat breakfast because they were the first ones that were listed in the problem. So the null hypothesis is mu1 equals mu2, or according to StatCrunch, mu1 minus mu2 equals 0. Now we have to think about the alternative hypothesis. So we want to know whether the students in group 2 have a higher mean than students in group 1. Well, that's the same as testing whether group 1 is less than group 2 on average. This means that the alternative hypothesis is mu1 less than mu2. Now that may seem counterintuitive because we were asked whether students who eat breakfast have a higher mean, so you might expect that to be greater than. But the inequality goes the other way in this example. Okay, so we have our hypotheses. H naught is mu1 equals mu2 versus HA mu1 less than mu2. And then for all of these, I'm just going to ask you to do it in StatCrunch. You don't have to do any of these problems by hand. So this is StatCrunch output, and I'll show you in the videos how to generate this output. But it tells you the p-value here is 0.0927. So you pull up StatCrunch, you'll input a bunch of stuff, and you get a p-value of 0.0927. So it gives you that, and then all you have to do is state the conclusion. We're always still going to reject H0 if the p-value is less than alpha, and they gave us 0.05 in this problem for alpha. Our p-value is not less than alpha, so we fail to reject H0 and say that there is not enough evidence to conclude that people who eat breakfast score higher than those who don't, on average. Okay? So that's our first problem. Previously, we had used, we'd had to decide whether to use Z or T in a problem, whether it's a Z test or a T test. For this unit, for this section, we're only going to use T. In real life, we really never know sigma. And for large samples, Z and T are practically the same anyway. So in real life, people really don't use the Z. So all this is to say that we'll always use T. So here's a second example. So we have an oatmeal company that wants to advertise eating oatmeal every day for a year lowers people's cholesterol more than Lipitor. So they're going to take a sample of people and randomly assign them to two groups. One group's going to eat oatmeal every day for a year, while the other group for a year is going to take a low dose of Lipitor. And so we have, these are our data points, and they specify that some people dropped out because they were in the oatmeal group, and who wouldn't want to drop out if it's the oatmeal group? Yuck. So anyway, the sample sizes aren't equal, but that's fine, they don't have to be. So what we're looking at here, each data value would be the number of points a person's cholesterol dropped that year. So this 12 here means that a person in this group, their cholesterol dropped by 12 points. So the null hypothesis is going to be that the means are equal. The alternative hypothesis is going to be that the oatmeal group has a larger mean than the Lipitor group. So if we call oatmeal group 1, Lipitor group 2, these are our hypotheses. And plug and chug into StatCrunch, and we get a p-value of 0.0039. And they didn't specify a level of significance, so we'll just use 0.05 by default. Therefore, reject H0 if p-value is less than 0.05, which it is. Therefore, we reject H0. There is sufficient evidence to conclude that oatmeal lowers cholesterol more than Lipitor. There's one other thing I need to mention here. If you see this here, it talks about there's an option for pooled variances. When you're doing a two-sample t-test, there's always the option for whether you want to pool variances or not. You would pool variances if you want to use the assumption that the two group variances are equal, the group standard deviations are equal. But we don't want to make that assumption, so we will never choose to pool the variances. Okay, so you never have to think about whether you want to pool the variances. We're never going to. All right.